Our speaker is Levent Tuncel from Waterloo. He's been here for the whole semester and he'll tell us about Primal-Dual algorithms for hyperbolic programming problems.
Thank you very much, Bernd. It's a great pleasure to be here. I thank the organizers for this special semester and for this workshop. It has been a wonderful, productive semester so far. And today I'll talk about joint work with Levent Vanderberg. From UCLA. And one of the nice things about talking about this work here first is that it actually started here when there was another special semester of activities in optimization about a year and a half ago. And I listened to Levent give a talk early in the semester. That was the second time I heard that talk, and there was something that I wanted to talk to him about the first time I saw the talk. So, and then after the second time, I couldn't resist. And then some exciting results ensued, and I like to share it with you. But I resisted my usual interior point presentation where I prepare 120 slides and bombard you like a ruptured fire hose with notation and other things, so that at least, you know, we can have this situation where there is this questions by boarding, so that people can have time to think about questions. So one of the fortunate things for me is that James already started with some notation, which is actually very useful, the same notation I've been using in my notes, which I think is the same notation that Jim Renegar will use in the next talk, because it's Jim's notation. So, so we'll have some notion of continuity here. Let's see if we can find more smoothness. Okay, so we're gonna start with polynomials in n variables. So let P be a homogeneous polynomial of degree, let's call it theta. So I have n variables, degree is theta, such that P is hyperbolic in direction E. And this is precisely to the point of PE being positive, the same definition I mean that James used. Okay, so I mean that PE is positive, and when you look at the scalar polynomial Px plus x minus lambda E, all the theta roots are real. Okay. And then we can define a map lambda from Rn to R theta, such that I'm gonna write lambda x as lambda 1x, lambda 2x, lambda theta x. And these are ordered. Lambda 1 of x is, if you like, greater or equal to lambda 2, greater or equal to lambda theta x. And what are these lambdas? Well, these are the roots. So lambda i's are the roots of P x minus lambda E. Right? So again, we are just refreshing our memories about how James defined things. And then he also defined this hyperbolicity cone. And as I warned you about me bombarding you with lots of notation, one way to avoid that is to abuse the notation. So we already saw that the hyperbolicity cone depends on P as well as E. at least the first time you define it, but certainly depends on P. So, but the thing is there's always going to be P, any P you like this. So I'm not going to write P, and I'm not going to write E. And if you're worried about E in almost all the applications, I want you to think about the example of the positive semi-definite cone intersected with an arbitrary linear subspace. And then your polynomial is the determinant, and your E is I, the identity. All right? And then these are the eigenvalues. Okay, so this cone running away from me is the set of all x's in Rn such that all the eigenvalues are non-negative as a vector. Every entry of that lambda of x is non-negative. And if you want to look at the interior of this cone, then the interior we're going to denote by double plus. And that will be precisely everything in this cone such that lambda theta is positive. Or all of them are positive, because lambda theta is the minimum of all of them. Okay, so this was the same kind of setup. So now we're going to move to these hyperbolic optimization problems. So we're going to say, okay, so let A some linear map from Rn to Rm. So this is linear. And some B that's in Rm, and some C that's in Rn be given. So this is our data, a triple. One is a linear map, and two others are elements of Rm and Rn. And then we have an optimization problem, which is to find the infimum of Cx subject to Ax equals B, and x is in the hyperbolicity cone. And in convex optimization, we always have at least one dual problem that's associated with every given convex optimization problem. In this case, I'll pick the conic dual. So the dual problem is defined, so this is a definition, as the problem of maximizing this linear form with dual variables y subject to A star y plus S equals C. So A star is like A transpose. It's the adjoint of this linear transformation. And S must be in the cone that is dual to our hyperbolicity cone. So this is the kind of animal we don't know as much about. We would like to know more about. But for the purposes of today's talk, you'll see that we know enough to have interesting algorithms. So notice that, so I'm not going to use the definition notation because I'm operating with the general definition of a dual of a convex cone. That's why I'm writing as an equality. So this is the set of all S's in Rn such that Sx is non-negative for all x in the hyperbolicity cone. Right. So I'm using capital lambda plus for the hyperbolicity cone, and you see the beautiful choice of notation by Renegar. These are the small lambdas. All right, so is the dual problem clear? Defined by the same data, and the dual cone is defined implicitly like this. Okay, so typically in interior point methods, at least the theoretical ones, we also assume that some x0 that is in the interior of the hyperbolicity cone and some s0 that is in the interior of the dual cone are given to us as starting points such that they're feasible. So Ax0 is equal to B, and A star Y0 plus S0 is equal to C. Now you might say, you didn't define Y0. What's Y0? Well, if you give me an S0 that is in the interior of the dual cone, such that it satisfies this equality for some y. I mean by y0 such a y. So again, I'm defining it implicitly. And in particular, if A is surjective, then that y is unique. Right? And you may assume A is surjective, right? Because you have a system of linear equations here. A is not surjective. You just preprocess this, and you will find redundant equations, or you'll find a contradiction to solvability of this. That's one way to solve hyperbolic cone optimization problems. Okay, not always successful. So we are okay with the setup, and these are really without loss of generality. So one of the nice things about this kind of assumption, even though it's a little bit too strong, it guarantees that both problems attain their optimal values, and those optimal values are equal to each other. So that's nice. And then we can go on and try to solve these things. And so one of the, yes?
You don't assume compactness of your feasible region?
Very good. The question is, you're assuming some kind of strict feasibility. Are you not assuming any compactness? No, I'm not assuming any compactness. But his suspicion is right. There's some compactness that underlies things. So what happens is that the set of optimal solutions actually will be compact in many cases, and you can use that. Okay, any other questions? Great. So this is an important moment in the algorithms. So we're going to define a function, and this function is going to be a function from Rn to extended reals. So we'll extend the real line tiny bit at one end. We'll allow plus infinity. This is something that we do in convex optimization analysis that's extremely nice and useful. And what is the function? Well, this is something that we also saw already in James's talk. This is minus log p of x if x is in the interior of this hyperbolistic cone, and it's plus infinity otherwise. So this is the function, and then this function has a lot of nice properties. So maybe I should start from the nice properties now before we forget. So properties of f we need /use. So first property is that the domain of this function is the interior of the hyperbolistic cone. So it's a closed convex function in the, so closed and convex function, and the domain of f, where it's finite, is the interior of the hyperbolistic cone. So it's there. So you might say, well, that's a weird way to say. I haven't seen convex analysis yet. I am in boarding class A or boarding class 1. And well, tell me differently. So then I would say, well, this is a convex function. And that definition you should know, and please look it up if you don't. And it has the property that if you take any sequence in the interior of the whole hyperbolistic cone that converges to a boundary point, the values of the function f tend to plus infinity. And you see from these definitions that on the boundary of the hyperbolistic cone, at least one of the eigenvalues, namely the smallest one, is 0. And then you see that this indeed tends to plus infinity. So it has got this nice barrier property. Okay. So this is a kind of thing that's really a minimum requirement in interior point methods to have your function formulate your set. So the second property I want is theta logarithmic homogeneity. Well, this is really makes the mathematics nice. There are ways of avoiding it, but then I have to replace it with something else. And it's really a simple property. And here we have it automatically. My polynomial is degree theta. It's a homogeneous polynomial. Therefore, if you look at the minus logarithm of, say, p of t times x, this is same as t to the theta times p of x. And you see that a term of minus theta log t will come out. So that is the definition of theta logarithmically homogeneous. But in terms of polynomials, it just means that I have a homogeneous polynomial here with degree theta. So every monomial, if you write this back to a monomial basis, it's all degree theta. So it's really trivial again. What is the third one? I saved the best for last. What is this? This is this function. I'm going to write it like this. And then I'm going to write it like this. So first of all, before I say the property, what I'm writing is that I'm looking at the first derivative of my function. So I should really be looking at a w that's in the interior of the hyperbolistic cone. And I'm taking the scalar product with some x. Okay, so what I'm going to say that this is convex for all x in the hyperbolistic cone. So now what I am saying is that I'm thinking about this as a function of w. Okay, so I'm thinking of this function as a function that takes w to this. And w is a function, its domain is the interior of the hyperbolistic cone. Okay, so this is it. So these are the three properties that underline the most sort of general algorithms that we have in this framework in joint work with Levent Vanderburg. And then we have some sort of special algorithms that will have more property that will involve sparsity. But this is it. So those of you who are experts, you probably expect me to do something about self-concordant barriers. I'm not going to do it. Jim already knows why, because these are enough. These are enough, and in fact stronger in some sense than self-concordance, because, for instance, if you read Renegard's beautiful book on self-concordant barriers, you'll see that he operates with this Dickin ellipsoid condition. These conditions essentially guarantee Dickin ellipsoid-like condition. That's the variance of the Hessian over the interior of the feasible region for essentially a larger convex set than the Dickin ellipsoid. So in that sense, these are actually stronger. And what is this convexity of this thing? I mean, this animal is not foreign to us. James is nodding his head, not because he's nice to me, he's also nice to me. But the reason he's nodding is because he used this precisely in his slides, right? He had this quantity twice. All right. So we have seen that animal. It's a key thing. And then we also know actually that this is a bijection. It gives a bijection between the interior primal and dual cones. But convexity of this is important. So maybe I should say a little bit more, since I said that's important. So first of all, that condition in this sort of global setting was first used, as far as I know, by Nesterov and Todd. And in many ways, we can look at their work from 97 and 98 as starting with just these axioms, not only for the primal cone, but also for the dual cone. So what that means is that you get these two automatically somehow for the Fanshawe, sort of the dual barrier, but this one you have to assume for the dual barrier. So if you do that, then you really have Nesterov-Todd set up. So you could actually do all of their theorems starting with this for both primal and dual barriers. So that's beautiful. So one of the results due to Güler in 1997 was that one of those sides you could generalize to all hyperbolic polynomials in the sense that it applies to hyperbolistic cones and this function. Okay, so let me say a little bit more about this condition. This condition is equivalent to what we call negative curvature. So So negative curvature, you can write this in terms of the third derivative. So it tells you that when you take the third derivative at any interior point of your hyperbolicity cone, and then now that's a trilinear transformation, you evaluate one of the arguments at any point inside the hyperbolicity cone, then that gives you a symmetric bilinear form. That symmetric bilinear form is negative semi-definite. Okay, so that's another equivalent characterization of this. But maybe Bernd mentioned geometry. We have to do more geometry. This is too much analytics.
So
all right. Oh, yes.
This is a free tensor.
Second.
No.
Second.
So this is the third derivative of f.
So there are three x's.
There are very good. So the question is, isn't this third derivative of f a three tensor? It's a three linear form. Yes. So I haven't defined the notation, so I have to explain. So if I wanted to evaluate this third derivative, I would need three directions from Rn, h1, h2, h3, and I would get a scalar from this tensor. What I'm doing here is that I'm evaluating it only along one direction. So then I'm getting, as a result, a tensor, essentially. Right? So I'm getting a bilinear form. It's a trilinear form. I am putting only one element, and if you like to be more formal, that's actually a good point. See, when I said I'm going to abuse the notation, I wasn't kidding. Pablo is keeping me straight. So what I mean is this, if you like.
Okay.
So there are two dots there that I am not doing anything to. So now I'm thinking of this as a bilinear form. And it's a symmetric bilinear form. It's negative semi-definite. Great. But then you notice that this guy is the Hessian of this guy. No, it's the negation of the Hessian of that guy. So if your function is 3 times continuously differentiable, it's indeed the same condition. But as I said, geometry. So what does it say about geometry? Equivalently, and this is perhaps the cleanest geometric condition. When you look at now the Hessian at any interior point of the hyperbolicity cone as a linear map, you fix a W in the interior and think about it as a linear map that maps the primal space to the dual space. And what it does is when you apply it to the primal hyperbolicity cone, this gives you a convex cone, and that convex cone is contained in the dual of the hyperbolicity cone. So this purely geometric property that's supposed to hold for every W in the interior of the hyperbolicity cone is equivalent to having negative curvature, which is equivalent to having this function as a convex function. Is that okay? Yes?
Can you clarify a bit what you said before, the relationship of this with self-concordance? I mean...
Right. Very good question. So Pablo says I said something about these things implying self-concordance and actually being stronger, and he wants more explanation. So self-concordance, we typically have this other condition that says that the third derivative is bounded by the second derivative with the right degree of homogeneity. So that's hence the word self-concordance. It tells you that the growth of the Hessian is regulated by its own derivative. So if the Hessian is small as an operator, then the changes in it will be expected to be small because the third derivative is bounded by the Hessian. So that's the condition. That's maybe not the nicest way of writing it. Since we're talking about the Hessian, then you could say, okay, I'm sitting at an interior point, x. I want to pick a direction, h, and I want to see how the Hessian changes along this direction. So equivalently, we can say that that change is bounded. So that is, so this condition leads to that change being bounded in a bigger set. And I'm going to draw a Mickey Mouse picture to explain it better. So for that, I'm going to define two things. So given H in Rn and, okay, maybe I should make a general statement first. In interior point methods, and many first order methods, we design, analyze, and implement algorithms based on local metrics. So each function like this induces a local metric with its Hessian at that point. So and that relates to geometry. So for all H in Rn, we can define this local norm with respect to some W. Let me just take the square. So I avoid the square root on the other side. So this is defined to be F double prime W H H. Okay, so then what we are saying is that when you look at the unit ball with respect to this norm, it's an ellipsoid, and the shape and size of the ellipsoid is determined by the Hessian. So this is one definition, and there's another definition that we should have. This is the Minkowski function. Again, measuring how H is. So one way to define this is as taking the, so there are many ways of writing it. This is what I like. X minus TH, W minus TH, W minus TH. So you're sitting at a point W, and you're looking at a direction H, and you're trying to find what is the largest step I can take from W in the direction of H, minus H, so that I stay in the cone. Okay? And smaller the sigma, the larger the step you can take with respect to H. So these two things geometrically are very important. So, well,
Do you want a minus on the F double prime?
over here, no. So this is a positive definite form, right? Because so this is not the gradient of this guy. This is just the Hessian of the barrier. So this is indeed always positive, and it has to be positive definite for it to define a norm. So let me describe some of the geometry, and oh boy, okay. So suppose that I do what James suggested. If you remember, he looked at these cones, and then he took these hyperplanes that were orthogonal to the direction of hyperbolicity. You don't have to quite take the orthogonal ones. You can take any interior point from the dual cone, and you'll have that kind of a geometry, and that's what I want to look at. I'm slicing the cone in a certain way, so that, say, maybe I'm looking at a point W, maybe it's X, and then I'm looking at this function. This is the Minkowski function with pole W, and I'm looking at what's the largest step I can take in this direction, what's the largest step I can take in this direction, and so on. I'm doing this. And then from this, I really want to define another norm. I'm going to define a cone norm with respect to the hyperbolicity cone and the point W, as the maximum of this Minkowski function, and also the same function for the other direction. So what does this do? So what this does is that it creates the largest centrally symmetric set that is contained in my cone that's centered at W. So this norm induces a ball, or the ball induces a norm, either way, right? And the underlying ball is the compact convex set, which is the largest centrally symmetric convex set you can put in the cone that's centered at W. So this is, in some sense, the best local approximation to your set. Best inner local approximation that's symmetric, right? So what is it about the other norm induced by the Hessian? So the unit ball for that guy, what does it look like in this Mickey Mouse picture? In that Mickey Mouse picture, or any other Mickey Mouse picture, it's always contained in the interior of your cone. Or in general, if you take the slice with the affine subspace, it's contained in your feasible region. So the usual self-concordance gives you this Dickin ellipsoid. It's this blue ellipsoid, and it's always in the interior, and you can use it to design and analyze algorithms, and they're typically going to be what we call short-step algorithms, whereas this convexity of that gradient function, or the negative curvature equivalently, or this beautiful geometric condition that the Hessian of this function maps the hyperbolistic cone into the dual cone all the time, guarantees that you could work with this largest centrally symmetric convex set as your approximation. So is the geometry sort of vaguely clear? So there are a whole bunch of norms that are going around, and in fact I'm not going to be able to analyze the algorithms theoretically in this talk, but as you can imagine, there are operator norms induced by this norm as well as this norm. And in fact, we can use the operator norms induced by this norm for tensors that come from Hessians or the third derivatives, and we can bound things in their natural domain with these things. Okay, so the general ideas I think are okay, but now I need to say a little bit more. I'm going to maybe do it from here. So James said in optimization, we propose a class of optimization problems, a family, and I will feel jealous if I don't do it. So let's do a family of optimization problems. Let mu be a positive scalar value, and then define the following family of problems. Let's call it P mu, which is to find the infimum of 1 over mu Cx plus f of x subject to ax equals b. So since the domain of f is the interior of the hyperbolistic cone, I can just ignore that difficult constraint when I do this minimization, because this function is plus infinity everywhere else, and I already know that there are solutions x0 that are feasible. So under these assumptions of x0 and s0 existing and a being surjective, this problem has a unique solution for every positive mu, unique solution x mu, s mu, and y mu for every mu that's positive, and that solution is characterized by ax equals b. X is in the interior of the hyperbolistic cone. A star y plus s is equal to c, and s is equal to minus mu f prime x. So these conditions imply that the corresponding solution x mu is feasible in the primal, corresponding solution s mu is feasible in the dual. Moreover, their duality gap x mu s mu is equal to theta times mu. So theta was the degree of our polynomial and mu was the parameter. But now we can turn it around and we can say for any pair of primal point x and dual point s, we can associate a mu by taking s, x, and dividing it by theta. So this set of unique solutions, x mu, s mu, y mu, define what we call central path, and it's a central object in interior point methods. And so then what we can do is we can generate algorithms where we choose our metric, local metric, very carefully, and we somehow loosely or closely follow the central path. So what are the okay, so very little time left. Question? No? All right. Okay, so then let me define a function. So local metric. So let's say local metric. So I'm going to define a function for any given pair of x and s as SW plus minus f primed w x. Okay, so notice that I define this, if you like, fix for all x in this guy, for all s in the dual. This is a nice function, and the most non-trivial part we have already seen and well done, which is this one, which we know is convex, regardless of how we pick x and s. So this function already appeared in a proof in a paper of Nesterov and Todd in the context of self-scaled barriers. This is how they show the existence of a metric, a positive definite metric that maps x to s, and it comes from a Hessian. Now, we can do the same thing under these assumptions that I described, because this function is convex. This new C is still convex, because this guy is just linear in W. And it's interesting that this function is well defined on the whole cone, not just the interior, but in the algorithm we work in the interior. So for instance, let me just give you a theorem to give you a taste of what you can prove about this result. So you fix x and s for every x and s like this, for all w in the interior of the hyperbolistic cone, we have the following results. So how should I do it? Well, let me just write the upper bound first. So this guy is upper bounded by 1 over 2 squared of mu. So let's define mu to be sx over theta like we did. So this, and then this, and then this, and then this. So this is the function that minimizers, so the minimizers of this function, minimizers w bar, satisfy f double prime w x equals s. So you just write the necessary conditions for optimality, use convexity, and you can see that not only that the Hessian at W maps the primal hyperbolistic cone into its dual, but actually it maps your specific x to specific s. And in the case of what are called symmetric cones, this actually, if the Hessian at W satisfying this condition gives you the largest pair of primal dual ellipsoids that are contained in the respective cones and that are centered at x and s, a theorem of Todd from 2009. So in that sense, in terms of ellipsoidal approximations, it is the best approximation to both primal and dual feasible region. Okay, so this, and then for experts, for non-experts who saw these local norms for the first time, this may look magical, but I think you can at least appreciate the simplicity. Simplicity. It's the local norm of X. This is the local norm of S. I am measuring it with respect to not the Hessian, but the inverse of the Hessian. This is the dual norm. So everything is happening in terms of the good barrier, and there is a lower bound in terms of, so that tells you how the analysis of such an algorithm might go. There's also a lower bound in terms of same kind of things. And the lower bound is SW star plus XW star. And then this is greater or equal to 2 times square root of SW star XW star. And this is greater or equal to 2 times square root of theta mu. So it just gives you some beautiful result that relates this kind of variational approach that determines sort of the best local metric to things in terms of the local norm defined by the Hessian at W. And you see that they are similar animals, and under some conditions they are tight, some other conditions they are not. So, but it just gives you a flavor of how this goes. So let me quickly tell you before I get the red card. I already got the yellow card. I should at least tell you the algorithm and the special. Oh goodness. Okay, I have to talk 3 times as fast, which people who know me know I can do. Okay, so the algorithm, I'm just going to say what it does instead of writing it. Algorithm minimizes this and finds such a W, if you like approximately, and then looks at how closely the central path equation is satisfied. If it's satisfied close enough, it uses this as the metric to find the search direction. If it is not, it does a rank 2 update that's sort of related to some work that I did in 2001 and then later with a student of mine, Mikela Bust, in 2014. And then that satisfies the central path equation for that metric. And then it computes the corresponding search direction and the step sizes. And the theorem is that it leads to many order of square root of theta log 1 over epsilon iteration complexity Primal-Dual algorithms which exploit negative curvature implied by hyperbolicity. So this is sort of the general setup, but the sort of, to me, the shock and awe part, I mean, I love the theoretical part, but there's actually a class of cones that we identified about a year and a half ago that are called homogeneous chordal cones. Special case. A very special case, but still strictly more general than Nesterov thought. Strictly more general. I am seeing the red card. So now I have to say what they are quickly. So these are the cones that can be expressed as a semi-definite cone intersected with the linear subspace where the sparsity graph does not contain a C4 or P4 as a node-induced minor. Does not contain C4 because it's chordal. Does not contain P4 because it has to be homogeneous. So there is one more theorem I was going to say, but I have the red card. So the theorem there says that such a metric decomposes into primal and dual automorphisms in a way that you can have what's called a V-space approach for such problems. And when it comes to this being a second order method, it works like a first order method because the Hessians of such barriers for homogeneous chordal cones are very fast to compute, not worse than the gradient. Thank you very much.
We will have time for questions and discussion. Of course, different airlines have different methods for deciding their status. So let's try something different. So if your average number is infinity, you are invited to ask a question. So if you disconnected from Erdős in the collaboration graph, you're
very
now
nice.
invited to ask the speaker a question. My measure of juniority.
The first level is you don't know what an Erdős is.
Yeah, or if you don't know who Erdős is,
So you're not allowed.
yeah, if you don't know who Erdős is, or your Erdős number is infinity, then you're now invited to ask a question. Everything clear? It's going to be on the exam. Okay, then let's try Erdős number 3 or more. So if your Erdős number is 3, 4, 5, something like this, you want to ask yourself a question?
Yes, I think it may be 2, but I'm going to just cut in front.
Okay.
So I have a question
To the speaker or
to the audience. So I listed these conditions for these barriers, and the thing is that I do not know whether every convex cone admits a barrier function like that which has negative curvature. So the most general class of convex cones which I know that admit such a barrier are the hyperbolicity cones. And we also have a calculus of such barriers. You can take their sum, which is equivalent to multiplication of the underlying hyperbolic polynomials. We can take restrictions to linear subspaces, again a familiar algebraic thing, and we can take linear preimages and direct sums, obviously. So that's a question that I have. I don't know if the class of convex cones which admit such barrier functions is more general than the hyperbolicity cones.
Okay, very, very good. So if you have Erdős number greater than or equal 3 and you're not the speaker,
Actually, yes. So from an algorithmic perspective, so what access for P do you need for to compute, or for?
Very good. So the question is, what kind of input format do you need for P to actually run such an algorithm? So we really need to evaluate the polynomial, and we need to evaluate its gradient at least. So with that I can do. So now, if we're writing a code, in fact we have some code, hopefully at some point there will be 3 codes or so I'm hoping for these things. In one of the codes what we have is straight line programs. So if you enter your polynomial as a straight line program, that's a circuit, you just tell me, in order what operations I need to do, then that's sufficient to run this thing. And if, as a result, for your polynomial, if you have a straight line program that runs in polynomial time in some, say, parameter that you picked as a graph or whatever the real input is, then this algorithm will run in polynomial time to produce an approximately optimal solution. But another thing I need is this E. I need this interior point in the interior of the hyperbolicity cone. But straight line programs currently is sort of the most common way. So what I would do is I would have an input setup where either it's a determinantal function or it's given as a straight line program. So those are the sort of minimal requirements that even in practice it works.
So, but you don't need to compute the roots.
Okay, so very good. Question is, how about computing the roots? Well, of course, I didn't even get into doing the line search and stuff like this. So there is a beautiful theory. If you allow me short steps, and if I do them well enough, I can actually avoid computing roots. Because I know from these theories that certain convex sets are included in my cone and so on. But of course, any practical algorithm will have to compute roots to relatively decent accuracy. And with sort of straight line programs, we can do that.
okay, why don't we open it up to everybody? So even if your Erdős number is 1 or 2, or if you are Erdős, or if you're Eldest, you can ask a question.
I'm neither of those. So for the straight line case, I mean, how do you ensure that you actually have hyperbolicity? I mean, what if I...
Oh, no. Oh, very good. Sorry to interrupt you. Your question is so good, I already maybe have more. But in any case, the question is, how can you say that it's, I said determinantal representation or a straight line program. Clearly, if you give me a determinant and you did it correctly, it is hyperbolic. That's okay. That's why Pablo says, well, what if somebody gave you a straight line program for a polynomial and it's not hyperbolic? So I guess I should have made that clear. Then I don't know. The algorithm would potentially fail. So I would need the user.
You don't need to certify the property as long as it's true.
Exactly.
The algorithm will.
Exactly. So that's a very kind remark. So Pablo is saying that, I am saying that as long as the user correctly verified and takes full responsibility for their polynomial for being hyperbolic, the algorithm will run correctly. But of course, they gave me an E that's not in the interior of the hyperbolistic cone, then it will of course fail. But
No, but
those are those kinds of users, yeah.
I mean, you may be able to randomly generate things that have this property with high probability, but you may not be able to certify them.
Yes. That's a very good point. So remark Pablo is making is that, well, you can randomly generate a straight line program for a class of polynomials managed any way you want in terms of depth and variation in the operations that you use, and then just experiment. And some of them might not even be hyperbolic. They might not even define a convex set, but at the end you might actually solve the problem by luck. And the thing is that they might be hyperbolic. It might even be NP hard or co-NP hard to certify that they are, but the algorithm might run. Nice remark.
Okay, any other? Yes, thank you.
What's the advantage of negative curvature over self-concordance? Like this iteration complexity, you can also get by short step methods, right?
That's right. In fact, the cleanest analysis, the shortest analysis somehow uses the minimizer of this function and then does this rank 2 update and bounds on the operator norm of the rank 2 update based on this big operator norm, and that's very clean. Okay, but that algorithm actually really generates things inside the Deakin ellipsoid. It really finds the optimal solution within the Deakin ellipsoid. It typically takes a corrector step in the next iteration to get close to the central path, or that it mixes what we call the affine scaling direction with the centering direction, but it stays quite close to the central path. But the advantage of this negative curvature is that the change in the Hessian can be managed in this big ball, which is essentially the largest nice approximation you can have to your set. So in that sense, you can actually take pretty large steps in the primal, the hyperbolistic cone problem. Now the issue is that, as I said, we don't know as much about the dual cone. And as a result, in these algorithms, you don't want to enforce complete primal dual symmetry. All you want to do is use the dual information. So in that sense, I didn't even define the Legendre referential conjugate of F. In some sense, I don't need it, because I know that F prime provides a bijection between the interior of this and interior of the dual cone, and I can do things in terms of just F primed. And that's the right way to do it. So in that sense, the way that we update the primal, which is based on this big convex set, and the way that we update the dual are different. So in that sense, the inside of the algorithm is not symmetric primal dual. But I call these primal dual symmetric algorithms because the algorithm is sophisticated enough that it applies all it knows on the easier problem. As a result, if you were to try to fool the algorithm by giving your primal cone as this, the algorithm would still solve what's called a hyperbolic heavy, in a hyperbolic heavy way. So there is an advantage.
Okay, so I suggest we thank the speaker. We'll meet again at 11:45 for Jim Renniger's talk. There's now actually a break.